Okay, now that we've made our journey through the land of linear systems of differential equations and come out the other end well versed in at least some aspects of linear algebra, and by the way, linear algebra is a big subject, so we only hit the pieces of it that we really needed for that theory. We're going to take some of that theory and return to the problem of second order differential equations. When we had you know, we learned how to solve second order differential equations, and we also learned how to incorporate what are called initial conditions. Initial conditions you should think of, or initial value problems you should think of as having a differential equation which tells you about the dynamics of a solution. Let's say the dynamics of a particle, for example, and maybe the differential equation is telling you about how that particle's position is changing with time. Then the initial conditions are a description of, let's say, the particle's position and velocity at some fixed at some fixed point in time. Okay. Boundary value problems, which is what we're going to study now, are to be contrasted with initial value problems in the sense that they don't tell you about what's going on at a specific moment in time. It tells you about what's happening at two different moments in the trajectory of the solution. So whereas initial value problems again tell you about what's happening in a very local region, just around a single point, boundary value problems are going to be more global in nature. It's going to make them more challenging, but also very, very useful because this boundary value problem stuff that we're going to study undergirds a lot of different applications, including things like heat transfer, wave mechanics, and also stuff like quantum mechanics. So, and if you ever have the opportunity to learn quantum mechanics, you should take it because it's one of the most fascinating, mind blowing, and enlightening experiences that you can have as somebody who is quantitatively and physically literate. And you should take that opportunity because, again, it is astounding. But let's learn boundary value problems. This is some math that's very useful for that story. So what is a boundary value problem? Well, we're going to study a specific one. It's going to look like this. X double prime plus lambda x is equal to 0. Now that's a second order differential equation. Lambda here is a number. It's a constant. So it's got constant coefficients. Okay. So this is not unlike what we would have studied a month ago. Okay. And in fact, you should know how to solve this. Um, but we're going to specify now what are called boundary conditions. We're going to have x of 0 equals 0 and or x of a, let me be more general, x of a is equal to 0 and x of b is also equal to 0. Oh, and I'll say a is less than b here just for, I mean, it doesn't matter, but yeah, we'll just specify that. So the way I want you to think about it is we're really keenly interested in pinning down the values of a solution at 2 points, A and B, which are different from one another. This, because those 2 points, A and B, are different from one another, we think of this as being a more global in nature type of problem. It's not just focusing on the position and the velocity of a solution at a particular point in time. It's more like we're needing to satisfy these two constraints which are separated in time. It's almost like a ballistics problem, right? Like we're firing a cannon at point A and we want it to hit a specific target at point B. That's a much more difficult problem than just understanding what's happening at a particular moment in time and then letting the system evolve according to a differential equation. Okay? So, unfortunately, we're not going to have nice results around the existence and uniqueness of solutions. Now, solutions definitely exist because you can see, for example, in this problem here, x equal to 0 is a solution. So if we take the constant solution x of t equal to 0, that's obviously a solution. But we think of that as being like the trivial solution. It's not very interesting. What we're interested in are non-zero solutions. And maybe there's something turning in your head a little bit because where else were we really interested in non-zero things? It's with eigenvectors and eigenvalues. Okay, this is going to come into play. All right, let's look at an example. Here is a good example of a boundary value problem. Let's look at x double prime plus x equals 0. And let's take x of 0 to be 0 and x of pi to be also 0. So to be clear, this is an example of a problem that of the sort that we have above. We have lambda equal to 1, we have a equal to 0, and we have b equal to pi. That's the sort of data of this problem. Okay? Now, what's the solution? Is there a solution? Can we write down some solutions? Yeah, absolutely. Okay, the idea here is we first find the general solution. The general solution. And this goes back to you thinking about the characteristic polynomial, r squared plus 1 equals 0, the roots of which are plus and minus I. And so there you have, if you think of the complex conjugate pair of roots as being alpha plus beta plus or minus beta I, alpha is 0 and beta is 1. So you can write down the solution from that. I'm going to write it as the general solution as a cosine beta is 1, so t, plus b sine of t. That's review. If you don't know how to do that, you better review. Okay, good. So that's x of t. Now let's think about what these initial conditions are saying. Or sorry, I called them initial conditions. What they are boundary constraints. Okay, let's think about what these boundary constraints are telling us. The first one says 0 is equal to x of 0. X of 0 is 0. Just wrote it in the other order. And if we plug in 0, what we learned, well, the b sine t dies. So we're left, and cosine of 0 is 1. So we just are left with a. We learned that a is 0, in other words. Okay. So to satisfy that first condition, we need a to be 0. All right. What about the second condition? That 0 would be x of pi. Oops. Well, when you plug in, well, we already know a is 0, so let's just ignore that. What do we get when we plug in pi to t? For t, we get b sine t, b sine pi, of course. Sine of pi is 0, right? Which is just 0. So b, the number b can be whatever it wants to be. Anything. It can be anything. Okay? So the solution, there are infinitely many solutions to this boundary value problem. So we have infinitely many solutions. And they are all of the form x of t equals b sine t. B can be anything because sine of pi is 0, right? A has to be 0, though, but b can be whatever it wants to be. All right, cool. So what is this sort of saying? It's saying something very simple. If I draw for you a graph, what we're saying is the following. That at x equal, so we give a specification for the solution at 2 points, namely at 0 and at pi. 0 and pi. Imagine that's pi. And we want the solution to cross the x-axis at these 2 points, 0 and pi. So what should a solution kind of look like? Well, if it's b sine t, then it's going to be some kind of sine wave that connects these two. Like this. You might imagine it looks something like this. Good. And what I can do is change the amplitude of this sine wave by moving by multiplying, adjusting the value of b. And you can see that no matter how I adjust b, just ignore that little vestigial tail. Wait, can I erase that? Maybe I can erase it. Like that. Can I? Oh, whatever. Oh, frick. Okay. But you can understand, as I adjust the value of b, I get a whole family of solutions to this differential equation, to this boundary value problem. Okay? Cool. Now, let's look at another example. Let's look at x double prime plus 2x equals 0 with the exact same boundary conditions. Okay? Then you can check, just as before, that the general solution to the differential equation alone is x of t equals a cosine square root of 2t plus b sine square root of 2t. Okay? Now, let's think about what the boundary conditions are saying. The first one says that 0 is equal to x of 0. That means I plug in t equal to 0. And again, that causes the a cosine, the b sine, the cosine square root of 2 times t term, cosine square root of 2 times t becomes cosine of 0, which is 1. So we're left with just a. And the sine term dies. Okay, so we learn that immediately that a is 0. Okay, a is 0. What about the second condition? That's x of pi. What is x of pi equal to? Well, a is 0, so let's forget about it. So that what we have is b sine square root of 2 times pi. Now, what you should know is that sine of square root of 2 times pi is not 0. Okay? Sine of x is only 0 at integer multiples of pi. So 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, etc. And it also negative multiples of pi. So negative pi, negative 2 pi, negative 3 pi, etc. It's not 0 in between. So this equation here tells us that b must also be 0. Okay? In other words, if we're on the hunt, if we want our boundary value problem to have non-trivial solutions for reasons, and we do have good reasons for that, I'm just telling you for right now, we do want that, then this particular boundary value problem does not have non-trivial solutions. We proved it. Every solution has to have a being 0 and b being 0. And so this implies no non-trivial solutions. How sad. Okay, so there's a difference here between these two problems, okay? What's the difference? Well, notice, maybe I'll show you the sort of specifications of this. For this problem, what is lambda? Lambda here is 2. What is a? Still 0. What is b? Still 0. So it seems like the difference between the green problem that we have here, this problem, where we did have non-zero solutions. See, look. And this problem here, where the only solution that we had was the 0 solution, was in this lambda. Okay? The lambda is different in each of these two problems. And that's what seems to make the difference. Interesting. Okay? So what we want to do is introduce some terminology for this. Okay? We're going to call these particular boundary value problems, we're going to call them eigenvalue problems. Okay? This is a typical nomenclature for these, okay? So we're going to call these eigenvalue problems. Don't freak out. All right, eigenvalue problems. And we are going to think about 3 different types of eigenvalue problems, all having the same differential equation, okay? But different boundary conditions. So I'm going to give you the 3 types. The first type of eigenvalue problem is what we just studied, or what we just looked at. X double prime plus lambda x equals 0, together with x of a equals 0 and x of b equaling 0. Okay, that's going to be the first type of eigenvalue problem. The second type will look like x double prime plus lambda x again. But now there's going to be a specification of the derivative of x at each of a and b. And the third type will be x double prime plus lambda x equals 0. And then instead of specifying that that either x or its derivative is 0 at a particular point, we're going to say that x of A and x of B should be the same. We're going to think of that as being one boundary condition. And we're going to say that a second boundary condition would be that its derivatives at A and B are the same. Okay? These are 3 different types of what are called eigenvalue problems. Okay? And we say, for each of these problems, we say, this is crucial, that lambda is an eigenvalue if there is a non-zero solution to the boundary value problem. Can I abbreviate or to the, yeah, boundary value problem. What? Gosh, this is so annoying sometimes. Boundary value problem. Boundary value problem. Okay. We call a solution, which is non-zero, an eigenfunction. So this is a really new terminology, an eigenfunction. So we have the notion of an eigenvalue, and we have the notion of an eigenfunction. Different eigenvalue problems, different ones of these, have different eigenvalues, and they're going to have different eigenfunctions, okay? Not unlike looking for matrices. Now, why do we call these, why do we borrow these words from linear algebra? Because really, it's much more common or typical to learn about eigen stuff is in a linear algebra context. Well, that's because if you think carefully about what's happening here, there's what's called a linear operator operating underneath the surface here. So if you just recall, back in the when we were talking about eigenvalues and eigenvectors, this was the eigenvector equation. PV equals lambda V, right? This was the eigenvector equation. Okay, but if you solve this this kind of differential equation here, x double prime plus lambda x, it's kind of like if you define L, okay, to be equal to, let's say, the negative second derivative operator. So I'm gonna just, if you don't like this, just relax, okay? If I define L to be this second derivative operator like this, okay, then I can rewrite this differential equation as Lx plus lambda x equals 0. Well, actually, negative Lx plus lambda x equals 0. And then I can, because I want to kill the negative sign that I put in the definition for L. and then I can solve this, okay? This would be something like Lx equals lambda x. And what I want you to observe is, oh my gosh, there is some kind of like structural similarity happening between these two green boxes. Do you see it? Lx equals lambda x. PV equals lambda v, right? That the effect of applying this operator, this second derivative operator, on this function x is simply to scale this function by lambda. This should feel a lot like the first green box, where we say that the effect of multiplying this vector v by p is to scale v by lambda. And just like in the world of eigenvectors and eigenvalues, we require that v, that vector, to be non-zero. We want that to be true about this as well. Okay, in the next one, we are going to do a comprehensive study of a particular eigenvalue, eigenfunction, eigenvalue problem, which is of real crucial importance for Fourier theory. Okay, and then hopefully in a third video, I'll be able to go through some of the details of why we care about framing it in terms of eigenvalue problems. Okay, see you in the next one.